This video is sponsored by PCBWay. Hello there and welcome back to another video. In today's video, I'm going to be building two devices, both of which perform the task of allowing you to reuse any old laptop power supply, or frankly, any old power brick, as an adjustable lab bench power supply that you can use to prototype all kinds of projects and run all sorts of useful tests on things. As someone who works with tech both personally and professionally, I've ended up in possession of a ton of old power bricks that go with devices that I either don't have anymore or that I never had, because I picked these power bricks out of old recycling piles. In any case, these power bricks are exceptional power supplies, being able to deliver several amps at pretty useful voltages a lot of the time. In fact, one of the ones I've got here is a whopping 130 watt power brick, which could power some pretty serious stuff. The issue is, and I'll use the 130 watt power brick as my example here, most projects I'm doing don't require the voltages coming out of these bricks. That, or the projects I'm prototyping, benefit from being tested at various voltage levels. So this 19.5 volt power brick ends up being really quite useless on its own. And the same goes for most of the power bricks that I end up with. Thankfully, working around this issue really isn't too hard, and it can be done with this simple module, a buck boost converter. This module allows you to input any voltage within its rated range, so in this case, any voltage between 5 and 30 volts DC, and then it can either step that voltage up or down to any voltage between 1.25 and 30 volts DC. Here I'm powering this module with my lab bench power supply set to 19.5 volts, which is a very common voltage for laptop chargers to output. Then, on the output of this module, I've got a big dummy load and these two multimeters that will give a readout of the module's output voltage and current. As we can see, we can get a pretty darn solid amount of power out of this thing, stepping the voltage up and down and drawing several amps of current. Plus, it's pretty darn efficient, because at almost 30 volts and 3 amps on the output, from 19.5 volts on the input, I measured 88.5% conversion efficiency. So I think that hooking this module up to the output of a power brick could absolutely yield a pretty sweet lab bench power supply. And so I took this module, a random power brick I had laying around, two 200 kilo ohm potentiometers, a small LED current and voltage display, two switches, a barrel jack, two binding posts, a diode, and a 3D printed enclosure to build up the first version of this project, which will convert any kind of power brick into an adjustable lab bench power supply. With all of the parts gathered, alongside some wire, heat shrink tubing, and some tools, I mounted the barrel jack into the enclosure with its included nut and washer. Right above the barrel jack, I added a small toggle switch, ensuring that it was oriented in a way that when the toggle switch was flipped upwards, the switch would turn on, and when it's down, the switch would be off. After these two components were mounted, I used a small piece of wire, in this case some decently thick wire that I pulled from an old PC power supply, and two pieces of heat shrink to connect the central positive pin of the barrel jack to one of the switch's contacts. Then, I soldered a small piece of wire to the barrel jack's outer negative contact and heat shrunk that connection too. Lastly, I also added a short piece of wire to the other contact of the switch with a piece of heat shrink, and this part of the assembly allows me to bring the power from the power brick into the device and toggle it on and off with the switch. Before I run this power into the input of the buck boost converter though, I have to do some other things first. One item on the agenda is potentiometers, because these converters use small trimmer potentiometers on their PCBs that have to be adjusted with a screwdriver to change their voltage output and current limit. But that's not what we want. We want knobs on the front panel of this device that can be turned with your hand. So I have to replace these trimmer potentiometers with some panel mount potentiometers of the same resistance value. Since these specific modules use 200 kilo ohm trimmers, I bought some 200 kilo ohm potentiometers and then soldered some extension wires onto them with heat shrink, of course. These potentiometers will later be soldered to the pads that the trimmers are currently installed onto, but we'll get to that in a bit. Before that, I'm going to get the output binding posts and switch ready, while there are fewer components in the chassis, making it less cramped. I mounted the two binding posts along with the output switch to the chassis, again making sure the switch was on when it was flipped upwards and off when it was flipped downwards. Once the components were mounted, I soldered a big fat diode across the output terminals in reverse, so that when functioning normally, no current would flow through it. Some of you may be familiar with the purpose of this diode, but for those who aren't, it's a reverse voltage protection diode. Say you're using this power supply to charge a battery, and you hook the battery up in reverse. Well, instead of cooking the buck boost converter, this diode, which usually isn't conducting any energy, starts conducting because the battery is wired backwards, and the diode is also wired backwards. This will short the battery out, which will protect the buck boost module, but the diode does generally die and need to be replaced after something like this happens. I chose a 1N5406, but basically any diode that can withstand a reverse voltage of 30 volts or more, as that's the max output of this power supply, will be fine. I would also recommend something that can handle a few amps of current too though, as it will get slammed hard in a reverse voltage scenario, and a weaker diode might fail open, meaning that not only will it die, but it will also fail to protect the module. With that done, I connected the positive binding post to one pole of the switch, and I also connected a piece of wire to the negative binding post. However, this negative wire was a mistake, as the first time I built this, I messed up a couple of things in regard to the wiring. So this wire should not be soldered to this binding post at this point. And now we're ready to place the buck boost converter in the chassis, but not before soldering the potentiometer connections for it. The first step to getting these soldered is to desolder the old trimmers, which can easily be done by applying a bunch of fresh solder to the area and moving the soldering iron back and forth to heat all of the pads at once until the old potentiometers fall out. Once the old potentiometers had been removed, I could tack the new potentiometer cables to the pads that were now free. I made sure to connect the pins in the correct order so that the potentiometers would work at all, but also so that their rotation direction was correct. This means that the left pin of the potentiometer went to the right pin of the trimmer, middle pin to middle pin, and right pin of the potentiometer to the left pin of the trimmer. I did this for both potentiometers and then mounted the pots to the case. I chose to place the voltage potentiometer, labeled on the board as CV, on the left, and the CC or current adjustment potentiometer on the right. But if you want this switched, you can do that too. Once the potentiometers were mounted, I then proceeded to mount the buck boost converter to the chassis with 4 M3x6 screws. Now that that's done, I took the 2 pigtails of wires from the current and voltage monitor display and started wiring them up to the correct spots inside the chassis so that they can later be plugged into the display. The 3-wire pigtail includes a red and black wire that carry power and ground for the display's circuitry, as well as a yellow wire that functions as a voltage probe. Also, a quick side note before I get into the wiring of these parts: what ends up showing up on screen and what I'm saying here are not going to line up very well. This is because I made some mistakes at this part that caused my power supply to be constantly shorted. I will tell you the correct things in this voiceover, but obviously still have to show something on screen while I do so. So just know that there will be discrepancies between what I say, which is the correct stuff, and what's shown, which is the incorrect stuff. Anyway, the red and black wires of the 3-cable pigtail connect to the 2 wires coming out from the barrel jack and its switch. This allows the display to be powered directly off of the input from the power brick and not the output of the converter. Make sure you solder these in a way that allows a nice piece of exposed wire to stick out, as these exposed bits of wire will be connected to the buck boost converter, which you can go ahead and do right now as well. Now we're going to hold off on connecting the yellow wire for now, and we'll move on to the 2-wire pigtail that should also have the thicker wires coming out from it when compared to the one that we just used. This is where the current that gets measured by this display passes through. And something critical about this display's design, and that's the reason that I messed up, is that both wires on this pigtail will have a very low resistance connection to ground. This means that you have to measure the current on the negative wire of your circuit, and cannot do this on the positive wire without shorting everything out. This was the main mistake that I made. So the correct way to wire this is to connect the red wire of this pigtail to the negative binding post, and then the black wire of this pigtail to the negative output terminal of the buck boost converter. Now we can go back to the yellow wire, where it's time to mess with the unconnected terminal of the switch for the output, as this is where this wire gets used. Remember, at this point, one terminal of the switch should be connected to the positive binding post, and the other unconnected terminal is where we will solder both the yellow wire and another wire whose other end will connect to the positive output of the buck boost converter. Placing this voltage measurement wire at this point in the circuit is really important, because while we would get a more accurate measurement if we placed it directly on the binding post, as that would allow us to account for any of the voltage drops caused by the resistance of the wires and the switch, this would mean that the output would have to be switched on to be able to see the voltage readout. I think that one of the main benefits of an on-off switch on the output of a power supply is the ability to connect things and then view and change the voltage output before turning the output on and sending the voltage to your circuit. So connecting the voltage probe before the switch will allow you to view the output voltage even when the output is switched off. Finally, we can plug the 2 pigtails into the display and snap it through the hole in the front panel. That wraps up all of the electronic elements of this build. And now, with the 3D printed lid and 4 M3x8 screws, we can finalize the mechanical elements as well. Plugging in a power adapter and flicking the switch on the back of the unit powers everything up, and we can see the voltage readout of the converter and the current readout that shows how much current is flowing out of the output. Adjusting the voltage shows up on the display, and when I hit the output switch with a load attached, we can see the current flowing. We can also limit the current by dropping the current limit potentiometer. However, it's important to note that unlike with a regular lab power supply, where you can see your current limit setting with no current flowing, with these modules, you have to draw a bunch of current from the output and then clamp the current to where you want it with the knob. In the end, I think that this thing came out really well though. And to my own surprise, I found myself reaching for it actually quite often when I need to run a quick prototyping test on something that I've built. For example, I used it to test out a circuit for a future project video where I was experimenting with a new motor driver chip and PID control code. Alright, that's one of the 2 builds for this video done. An Instructable will be linked in the description for each of the 2 builds in this video if you want to make one of them for yourself, but really fast before I push forward into the second version of this project, I want to address the barrel jack issue. What barrel jack issue? Well, I say that this is compatible with basically any wall wart power adapter, and electrically this is true. However, the 5.5 by 2.5 millimeter barrel jack I chose might limit your options physically. Or does it? I chose this size because it's a very standard size, so it should natively fit many adapters, but some adapters, like the 130 watt Dell one I talked about at the start of the video, won't fit into this plug. However, the great thing about using such a common size DC barrel jack is that generally you can find little adapter dongles to convert whatever power supply you want into a 5.5 by 2.5 millimeter barrel jack, therefore allowing you to use it with this project. The only thing you need to be careful of at this point is any power supply that's got a center negative connection, as these will blow up the converter if plugged in. These aren't super common, but a good example of them are guitar pedal power supplies, which are very commonly center negative. Alright, and with that out of the way, let's move on to the second version of this project, which is, well, what is it? It seems like this first version is just fine. The second version of this project takes a much more DIY approach to the whole idea, with a custom voltage and current measurement system, which, while giving up a little bit of accuracy because it's not calibrated, does allow the readout to update a lot more frequently, which, believe it or not, is a crazy quality of life improvement when trying to set your voltage precisely. Additionally, this version has a fan for active cooling because the module does get hot enough in the other version for me to consider it not good for higher power applications. Furthermore, version 2 has a dedicated 5-volt rail output available on it alongside the variable output, and both can be used at the same time. And finally, due to the weirdness with current limit setting on these modules, I implemented a switchable internal dummy load into this version, which allows you to easily set a current limit without having to come up with some random way of loading the power supply every time you want to do so. Of course, this version is more expensive and component heavy, and therefore can't be built using a mere $20 or $25 worth of components like the first version can. But if it sounds cool to you, stick around to check it out. For this second version, the heart of the power supply is the same buck boost converter, but at the brain of the power supply is a custom PCB that I designed and ordered from today's video sponsor, PCBWay. PCBWay is a company that offers high-quality custom manufacturing services. Their portfolio includes a wide range of options such as PCB manufacturing and assembly, CNC machining, whether that's 3-axis, 5-axis, or turning, and 3D printing with a wide range of materials and processes available. All of these services have been made incredibly easy to use, and uploading your design can be as easy as just a few clicks uploading your zipped folder of Gerber files, or if you want something machined, it can be as easy as uploading a step file and calling it a day. I've used a ton of PCBWay products in my projects over the past few years, and they've never failed to make my builds so much more professional feeling, and at times, possible at all. I mean, there are sometimes things that just can't be built on a prototyping board. If what PCBWay does sounds interesting to you, check them and their services out at my link in the video description, and thank you again to them for sponsoring this video. After my PCBs arrived, I got right to work assembling them with all of the components necessary. I tried to consolidate as much of the power supply onto the PCB as I could, as I really don't enjoy having messes of wires inside of the chassis of my projects, though it does always seem to end up that way. In any case, I put as many parts on here as I could, such as the reverse voltage protection diodes, the dummy load, the converter for the 5-volt rail, and the voltage measurement circuitry. The main parts that couldn't be put on here are anything that's on the front panel, the main converter, and the current measurement sensor. I used an ACS 712 sensor for this project, and while I have used these as regular SMD chips before with great results, I chose to use an external sensor board because I don't want to scare anyone off of this project by using an SMD part that has to be soldered by the user. I soldered every part of the PCB together except these 4 resistors, as these build up voltage dividers that measure voltage on the output of the power supply. The exact resistors that go into these spots need to be measured before they're soldered into place, as even the discrepancies that can be observed in a 1% tolerance resistor can throw off the voltage readings massively if not accounted for. So I measured each resistor before putting them into the board and wrote the readings down. Down the line, I did have to change out the 20 kilo ohm resistors for 12 kilo ohm resistors because I calculated the values needed wrongly. But when I did that, I still measured them to make sure that the values could be entered into the correct spots in the code and taken into account when calculating the voltage for maximum accuracy. With the board soldered together, I moved on to creating the heatsink for the 2 linear voltage regulators on the board. One regulator is an L7812 for the control voltage on the main PCB, and another is an L7805 for the 5-volt rail. I chose to use a random heatsink I had laying around for this that I just modified with a little drilling and hacksawing, but the heatsinks I specify in the instructable will just need 2 holes marked, drilled, and tapped. Now I wrote the code for the board and uploaded it to the Arduino, as doing it at this point would make it a little bit easier. However, if I did have to edit anything on the code, it was pretty easy to just unplug the Arduino from the board and reprogram it on the computer. Anyway, I moved on to the overall assembly now, and while I'd love to go over it in as much detail as I did for the previous build, I'm not going to run through the wiring as much as I did on that one. Otherwise, this video would end up way too long. So if you're looking for those details, go check out the instructable for this version of the project linked in the description. I first prepped the buck boost module by desoldering its pots, and I soldered extension wires to the new pots, but I didn't connect them to the module just yet. Before that, I started working on mounting and wiring up the barrel jack input as well as the main on-off switch. After that, I soldered the new pots onto the buck boost module and mounted that whole assembly into the case, tightening the potentiometers to the front panel and mounting the module with 3 M3x6 screws. I ended up using 3 screws here because I was running low on M3x6 screws, and 3 screws is honestly plenty to keep this secure. With the converter mounted, I moved on to mounting the main PCB in the case as well, and once it was screwed in with another set of 4 M3x6 screws, I connected the wires from the main power input to the barrel jack in connector on the main PCB. From there, I connected the connector labeled to buck boost converter to the input of the buck boost converter with some wires. And then I made another wiring mistake in this video by connecting the output of the buck boost converter straight through to the from buck boost converter header on the main board. I forgot to wire the current sensor in line with the positive line for this connection. Man, I gotta stop doing these projects late at night. In any case, I then began to work on the front panel, where I mounted the current limit dummy load switch to the case and used a couple spare resistor legs to connect it to the correct spot on the PCB for it. After that, I mounted the LCD display with 4 M3x16 screws that should have actually been M3x12 screws, and then I tightened some nuts on the back of the LCD. Next, I mounted the 2 binding posts for the 5-volt output, and ignore the weird color choices here. I bought a 5-color pack of binding posts forever ago and used all of the red and black ones. So I've got yellow, green, and blue left, and wanted a different color than yellow for the 5-volt output's positive terminal to differentiate it. So just know that green is ground, and in this case, I know it's weird, blue is positive. I also mounted the toggle switch for this output to the front panel, and then connected the negative binding post to the negative 5-volt output from the main PCB. Finally, I connected the positive binding post to the switch, and then the other pole of that switch to the positive 5-volt output on the main board. Finally, I took one more wire and soldered it to the 5V output's positive binding post, and then connected the other end of it to the 5V out sends connection on the PCB. This allows the Arduino to know when the 5V output is turned on, and it uses this to change what's displayed on the LCD and turn the fan speed up to cool the linear regulator. Next up, I moved on to assembling the adjustable output's front panel bits, those being the switch and binding post, and I began to wire them up. I did some really stupid stuff at this point in the wiring, probably because it was about 1 in the morning and I'd had a long day, but I should have hooked it up so that the negative binding post goes straight to the negative terminal on the main board. Then the positive output of the board also goes straight to the positive binding post. And the switch connects to the 2 contacts on the board for the main output switch, because the main output is controlled with a relay instead of being directly controlled through the switch. Then I should have connected the current sensor in line with the wire coming from the buck boost converter instead of the wire going to the positive terminal, as this allows you to actually see the current draw when using the internal dummy load feature. You know, kind of an important aspect considering the internal dummy load is there to help you set a current limit. In any case, I fixed all of this wiring at a later time, and for now, I hot glued the sensor to the case and plugged it into the motherboard with some standard DuPont cables, just as I had with the LCD. One of the last parts of wiring this build is to, just like on the 5V output, take a wire from the adjustable output's positive binding post and connect it to the connection labeled output voltage measurement point. This allows the unit to switch between measuring the voltage closer to the buck boost converter when the output is off, so that you can see what your set voltage is when the output's off, and then it can switch when the output is turned on to measuring as close to the output as it possibly can for that maximum voltage readout accuracy. Lastly, I mounted the 80mm cooling fan to the top lid with 4 regular fan screws, and then connected its positive and negative cables to the fan output on the PCB. I did have to cut out a small part of the fan's frame so that it would clear the 5V channel's toggle switch, but this seems to have no negative effect on the fan itself. And once I'd closed the unit up with 4 M3x8 screws, I was ready to test it out fully and talk about the features of it. So now what I'll do is I'll run through all of the features of this unit and why it's definitely nicer to use than the other, simpler one, while of course having its own set of downsides. First off, the voltage display is so much more responsive. This thing makes it actually doable to get a voltage relatively quickly, and man is it a good upgrade. Of course, the adjustable output is switchable, as it should be, and when it's toggled on, you can see on the LCD the voltage readout switches from set voltage to out voltage, corresponding with the system's switching measurement points for maximum accuracy. The voltage and especially the current readouts are not the most accurate things in the universe, though the voltage readout does generally end up relatively on point. I think a large portion of the current readout's inaccuracy is due to the fact that I used an ACS712 breakout module, which likely uses a fake ACS712 chip. I've used the real ones in previous projects and have been able to get much better results than this, so this explanation at the very least makes sense to me. Additionally, as one would expect, the 5V output is pretty much perfect as well, considering that it's coming from a basic linear regulator. This rail is really only good for about 500 milliamps though, due to the heatsink size and how much heat will have to be dissipated by the regulator with a power supply in this build's accepted voltage range. Speaking of the compatible input voltages for this unit, this is one of the downsides compared to the first build. This unit, due to the nature of the circuit design in it, really shouldn't be fed anything less than 15 volts, meaning that this build will mostly be limited to the spare 19.5 volt laptop chargers you have, and maybe the occasional 24 volt LED strip power supply as well. The other version is really good to take any input between 5 and 30 volts, so that one has a much more compatible voltage range. Moving on to the current limit setting helper, you can switch this mode on and draw a bunch of current inside the power supply to set your current limit. When this mode is entered, the adjustable output is switched off automatically, the fan goes to max, and you get 20 seconds since enabling it initially to set your limit. After 20 seconds, the unit will lock you out of this mode for 60 seconds to let the resistors cool down, as the majority of the time you will be severely overpowering the 3 ohm 5 watt bank, and so they need some serious cooldown time. This mode seems like it works well, but sadly it also seems that the particular buck boost module I got for the second build is a little messed up, as it doesn't like to listen to its current limit setting and also doesn't go up to 35 volts like the other one does. Plus, the other one's current limit seems to work a lot better in general, so that's a bummer that I might have gotten a bit of a lemon of a buck boost converter. especially because it makes showing off this feature quite difficult. The final major difference that I want to point out between these two builds is that this second one is much more suitable for continuous, high power applications, as it has active cooling and doesn't get super hot. The other one, however, will overheat if asked to output, say, 100 watts for 15 minutes straight. In all, I think that both of these versions of this project achieve the initial goal, with some advantages and disadvantages to both, of course. If either of these intrigues you, go ahead and check out the instructable links in the video description for full, detailed instructions on how to build them. Well, that's all that I have for you in this video. I hope that you were able to at least enjoy it, and maybe even learn a thing or two. In any case, I hope to see you next time. Goodbye.